this video, we are going to summarize what the rate of change looks like in different tables for linear functions. So we're going to continue to look at rate of change for linear functions in table of values. Go back to your anchor notes that are in the front of your binder that we took at the very beginning in lesson 1. Today we're going to add some details to summarize what we've done so far, and we're going to flag these pages so you can use them easily on your test this week. Looking at the first page in this lesson from the beginning, your anchor pages, I'm going to zoom into the bottom of that page where we're looking at the tables. Your notes don't say rate of change right here. I added that in. We're going to add a little detail of rate of change, and then on the next page, we're going to add some details. So in every lesson that we've had in this unit, we have been reminded that rate of change is the same thing as the change in y over the change in x, and if it's constant, we know the function is linear. And we get that information of the change in y over change in x by looking at our table of values. I will note that this little triangle is the Greek letter delta, and that means change. You'll often see this in math and science classes. And so we sometimes write it out in a longer way, our rate of change. We can write it out that it is the change in y over the change in x. And the last thing to mention here is that the rate of change must be constant for the whole table in order for the function to be linear. So your first page should look like mine. Flip over your page and you should see a page that looks like this right here, where we have 3 scenarios for rates of change. Find this page. So we're going to go in a deeper dive on rates of change. There are 3 ways you need to recognize rate of change in a linear function, and there's an important skill that we need to master. That skill is simplifying or reducing fractions or ratios. Fractions and ratios are the same thing. They can look the same way. We think of them as ratios because it is change in y over change in x, but in essence, they are simply a fraction. So to determine the rate of change, you must be able to compare the change ratios. To do this, all of the ratios or fractions need to be in simplest form. That means that the numerator, that's the top, and the denominator, that's the bottom, cannot both be divided by the same number. Let's look at a couple of examples. We're going to look at these 3 fractions and reduce them to their simplest form. So looking at the first one, and I'm going to just zoom in so it's easier to write, we're going to look at 20/4. And we can think of what divides in there evenly. And some of you might just see they're both even, and you could divide the top and bottom by 2. Some of you might recognize that 4 divides in there. So there's many different ways to do this. But if I recognize that 4 divides in there, I can divide 20 by 4, and I can divide 4 by 4. 20 divided by 4 is 5. And 4 divided by 4 is 1. So 20/4 is equivalent to 5/1. Let's zoom over to that middle problem. And again, you could look at this 2, these 10 and 2 are both even, so you could divide by 2. So if I take 10 divided by 2, I have to divide the denominator also by 2 to keep it equal. 10 divided by 2 is 5, and 2 divided by 2 is 1. And finally, if I look over at this 18/4, in the previous examples, the denominator or the bottom divided evenly in the numerator, so we could just check that. In this case, this doesn't work that way. 4 does not divide evenly into 18. It divides evenly into 16, but not 18. So we got to go smaller than 4. So because these are both even numbers, divisible by 2, I'm going to divide the top and bottom by 2. 18 divided by 2 is 9, and 4 divided by 2 is 2. Now we're looking at example A. We're going to always start with the change in x and the change in y. The description here says the change in x is 1 and the change in y is constant. This is the first of 3 scenarios that we're going to look at. Please complete your changes in x and your changes in y. So you can see in this scenario that says the change in x is 1. Now ours is -1, but it will behave the same way. And the change in y is constant other than 1. So you can see it's -6 for each of the changes. It is not 1, but it is constant. It is the same. And so when we look at the rate of change, we don't need to do a rate of change ratio for each one of these, because if we do the change in y over change in x for any pair of these, they are going to be identical. So we can tell already that this is going to be consistent or constant, and that means this is a linear function. You can leave your unit rate as a constant -6 over -1, but you will most likely see it simplified. -6 divided by -1 is the same as 6 over 1, and that's just more common in math. That is also our unit rate because it is per 1, so our unit rate is also 6 over 1. And so because we see that it is a constant unit rate, we confirm that this is indeed a linear function. For scenario B, the change in x is constant and the change in y is constant, but not necessarily 1. Find the change in x and change in y for the tables. So here you see that the change in x for the whole table is decreasing by 3 and the change in y is increasing by 4. So the change in x is constant and the change in y is constant. Let's find the rate of change, recalling that the rate of change is always the change in y over the change in x. And so when we look at our table, there's only one that we need to look at because they're all going to be 4 over -3. Because each change in y over change in x is identical, we can say that they are constant, which means that it is a constant rate of change or a constant 4 over -3, and that this table represents a linear function. Let's talk quickly about unit rate for this scenario. This scenario can have a unit rate that comes out to an integer. This particular one does not. It has a unit rate that comes out as a decimal. And I can see that because when I divide 4 divided by -3, 3 doesn't go into 4 evenly. So when I divide this on a calculator, 4 divided by -3 would come out to -1.3 repeating. We can write that as a fraction. It's going to be 1.3. You could put 1.33. You could put 1.3 with a bar across the top of it to show that it's repeating. But the key point here when we're talking about a unit rate is that it's got to be something over 1. And all you have to do is take your change in y and change in x and divide it out and put that over 1. Now, when you have different values here, you want to do that to really make sure it's constant. In this table, when the values of change in y and the change in x are exactly the same, we know it's constant. In scenario C, in our third scenario, the change in x does not look constant. The change in y does not look constant. So just when you look at the table, they do not look constant. I'm going to cross off this right here as a little typo. Looking at our table here, we see that we have change in x are all different. 1, 2, 1, 4, and my change in y, 5, 10, 5, 20. This may catch your eye because you do see some pairs that match up in here. But even if it doesn't make you think, oh, maybe this is linear, you should always calculate the rate of change. And you're going to do that for each one of these pairs. So you're going to be taking 5 over 1 for this first one. You are going to take 10 over 2 for the next one. We don't have to write 5 over 1 again because it is the same as the one above. I'll circle it in the same color. And then finally, we have down here 20 over 4. for our change in y over our change in x. And so our job now is to look at, do these come out to the same equivalent fractions? Can we reduce those? 5 over 1 cannot be reduced. It's already a unit rate. I'm going to write that right there. Because it's over 1, we know it's the unit rate. 10 over 2, I can divide 10 by 2, and I can divide 2 by 2, and that simplifies to 5 over 1, which is the same unit rate. For 20, I can divide that by 4, and I can divide 4 by 4. That 20 divided by 4 is 5, 4 divided by 4 is 1. And you can see that we get the same unit rate for all of these, so this is constant. So my rate of change is a constant 5 over 1. That is also my unit rate, and that means that this is a linear function. Even though at first we might not have noticed that they were the same, because when I look at my change in x, I'm seeing these different values. It's not coming out, it's not obviously the same at first, but when you find your rate of change, you will see that they simplify to the same unit rate, which is constant, and that means it's a linear function. So quick summary of what we've written. Always the rate of change is the change in y over change in x. Linear functions must have a constant rate of change. We must find the rate of change before determining if a table represents a linear function. You can't just tell by looking at these values, the change in y and the change in x. You have to calculate the rate of change. You must simplify the rate of change before determining if it's constant. You need to simplify like we did right here to see that they all come out to the same ratio, and they have the same unit rate, which means they're constant.